Okay, morning everyone. Okay, this is the second lesson in the SQL Foundation. Right, today we're going to talk about the different data types that we've got in SQL Server. Specifically, we're going to talk about system data types. But in SQL Server we can create custom data types as well, but we're not going to talk about them today at all. Then we're going to basically look at what the relational data model actually is, and who kind of came up with it, and what the concept is actually based on. And then we're going to look, well, basically we're going to discuss normalization and denormalization of data, and look at primary keys and foreign keys with some examples, basically. Okay, it's worth noting that we're going to look at normalization not in academic point, not from academic point of view, because academic point of view is rather boring, and I think it's a bit divorced from the common sense and the reality of it. So we're just going to basically take the table from a normalized state to a normalized state, just straight in. Okay, so different data types that we've got available in SQL Server are pretty much numeric, so they're exact numbers, approximate numbers, things like floats, etc. Datetime, strings, and character fields, binary, XML. It's an addition that's been added, I think, in SQL Server 2000, and it's not very well managed, I think. Also we can create our own types in SQL Server, such as, for example, we can create tables that act as data types, or we can create our own sort of combination of, let's say, datetime plus some strings and so on. Okay, so the first one we're going to look at is the numeric data types. We've got 4 basic numeric types, so this is the exact numbers, and they kind of range from well, some tiny integer, which is just takes a 1 byte in storage and gives you the range of available values from 0 to 255. Then we've got small int, which is a bit bigger. It only takes 2 bytes in the storage. Integer is a default value in SQL Server, and it gives you about 2 billion, the range of about 2 billion values, from minus 2 billion to about 2 billion, which is about 4 billion. And it takes 4 bytes in storage. And we've got big int, so as the name suggests, it's a big integer, and the number, but basically the range is quite huge, and it takes 8 bytes in storage. So the most common numeric type that we see in SQL Server is integer. This is what we use to normally identify the rows, unless your database will grow beyond 2 billion records, which is unlikely. However, if it does, then you need to sort of consider using big int as a unique identifier for a row. Okay, but generally, we also can talk about the conversion from one type to another, and the way the SQL Server handles conversion is got like preceding table, I think. So preceding table is basically a conversion order. For example, if we look at, if we're trying to convert big tiny int to integer, it will work because integer is bigger than tiny int. Or if you're trying to convert int to tiny int, if the range basically is over 255, then if the value is over 255, it will fail, basically. The same applies to data types, well, all the other data types. There's a preceding, well, I think it's called preceding conversion order on Microsoft website. You can see how the data gets converted. Also, it's worth noting that if you're trying to convert, actually we're going to talk about it in a minute when we look at decimals. So decimals is a data type, also kind of relates to precise numbers, because it actually stores the data in precise format. So what it is just is it called full part of a number, and then decimals after that. So it's declared in SQL Server as decimal, P and S, P being precision and S being a scale. So numeric data type is exactly the same, so it's a function of the denominator for decimal. So you can use either decimal or numeric data type, they're exactly the same. And basically it's got different precisions, and if the precision is from 1 to 9, meaning that the length of the number characters basically in that number can range from 1 to 9, including decimals. The storage it takes about 5 bytes, about exactly 5 bytes in storage, and some other precision. So the storage basically based on this precision. So P is the actual scale of the number. So if I declare a decimal number, decimal data type of 5, for example, then it means that I can have maximum of 9,999 numbers in it. Well, the number of 9,999. If I declare it as 5 precision and so let's say 2 a scale, the 2 is the number after decimal point. Right. Here we can actually go and look at an example. So open up SQL Server. I've got the dummy database set up where we can go and create different types of numbers and just basically look at its values. So there you go. First of all, I'm going to create a table, and within that table there's going to be multiple columns of different data types. So we're going to look at exact numbers first. So big int is basically big int, small int, and integer. Let's create a table, and what I'm going to do is insert some data into it. As you can see, the first big int, I'm going to insert a very large number. The second one is just within that range, and so on. Okay, so that's our result. So for example, if I try to insert data that is outside of the allowed range, let's say for 255, I'm going to try to insert 256, it will give us an overflow error. So there you go, arithmetic overflow. Okay. Now, where's my decimals? Okay, here's a decimal example. Okay, so exactly say if I declare a table and put some column of specific data types, so you see decimal, 5 being the total length of total, is that length? Yeah, I suppose it's a length. The total length of the field, and 2 is the number of decimal places I can have after, basically in that number. And what I'm going to do is going to go and insert some data into it. There you go, and get the data out. So as you can see, can I do zoom? I probably can't. Anyway, so what I'm getting back from the SQL Server, even though I'm inserted to 123, I actually get back the number with the decimal point. So if I then try to insert something like this, and get some data out, as you can see, insert decimal place in there. If I then try to insert something daft like that, which basically doesn't fit in our field because of the precision number, I still insert data, but the value would be rounded up to the nearest decimal point. Right, so, and to make it SQL Server treats those two fields as different data types because their precision is different. The way it actually converts, in order to basically combine those two fields, it needs to do a conversion, and it does the conversion based on that preceding table, preceding order, and the preceding order will be the data type with the largest scale, effectively, or the largest precision would be will take precedence over the lowest one. So, give you a little example. If I then combine the lower precision with higher precision, I will get a higher precision overall. There you go. So it basically combines, it takes the highest precision numeric value and combines it with the lowest one. I'll have to go through all of this again. Okay. The next data type is called float or real. It's called approximate numbers. That's because it uses a floating point, so it takes up less space in the database, but it means that the numbers are actually approximate, so it doesn't guarantee that the number you actually insert in it is the number you're going to get back, and it stores everything in some weird format in there. I forgot what it's called. Anyhow, you've got different types of precision in there, meaning that the length, the basically the number it can store up to 7 digits. It will take 4 bytes, and then up to 15 digits. It'll take 8 bytes in storage. Basically, there's no point actually doing an example of float. Because it's actually pretty simple. You just declare a table with a float, insert some data in it, and that's it. If you insert a whole number, it will get a whole number. You can insert a whole number with a decimal place in it. Well, if you insert a number with a decimal place in it, you get something like, the whole number dot then 99999999991, something like that. So the next data type, which is a little bit more interesting, is called data type. And data type, SQL Server actually allows us to have got multiple data types for date and time. And the most commonly used one is date time. That field over there actually allows us to store date and time in the same field. It takes 8 bytes, and basically it's got a precision as well. So precision is up to 1,000ths of a second, and each is actually it's rounded to the nearest third second, no, thirds of 1,000 of a second. So, well, I'll give you a little example. Then date itself just takes 3 bytes, and guess what? Time takes 5 bytes, overall 8 bytes, and time on its own can store up to 100 nanosecond precision. SQL Server 2005 added a new data type called data type 2. Basically, the whole point of data type 2 is having a larger precision, such as it can go up to 1 millionth of a second, and it also takes less space in storage. For example, we don't use data type 2 because of SQL. Actually, we can use data type 2, but there's no point because we don't need that much precision out of the data type itself. The only benefit there is that if you use lower precision, specifically specified that I want to use lower precision, it takes a little bit less space in the database, which is good if you index by data time. But okay, the other quite useful data time data type in SQL Server is called data time offset. And that's basically a data time with offset from the UTC data time. So, for example, imagine you want to insert some data into a data table, but from different, basically from different time zones. What you do is you insert the data as the local time, and then you specify the offset from the UTC. So, for example, insert that, well, right now, for example, we are 1 hour of the UTC, so we'll insert that it's 8 o'clock in the morning, or something like that, well, 10 past 8, minus 1 hour, basically. Okay, let's have a look at the example. Right. Create a table first with different data types and insert some data into it. As you can see, the first data time, I'm just going to insert, by the way, all the formats in SQL Server is suggested to be a so-called ODBC format, where we've got year dash months dash day. If you use anything else, you're going to get yourself in a bit of a trouble. And we can also, SQL Server allows us to define what date format we're going to use with a setting called set date format, and then we specify year, month, date. We can instruct this SQL Server to basically reverse this order. Americans, for example, would do something like that. They would put year, months, and year, date, and months, or something like this. Day and months, which is daft. Anyway, so can we create this table? I have. Okay. In the first field, I'm just going to insert the date, and as you can see, I'm going to insert the time with 2 basically thousandths of a second, and we're just going to see what we're going to get back out of it. We're also going to insert just the time into a time column, and we're also going to insert the time with 2 thousandths of a second into datetime2 field, and this is basically stating that we basically datetime offset. We're going to insert date that today, right now it's 11 o'clock in the evening, 10 past 11, and our offset from UTC is plus 2 hours. So the UTC time is 21 hours, 10 past 9 actually. Okay, let's get some data back. So, as you can see, because we've got precision point of basically every number in every millisecond part of the date time field is rounded up to the third. Basically up to the third, 1/3 of third thousandths of a second. I don't know how to say this. Huh? What? It's too clever word for it. All right. So basically, as you can see, we inserted 0.002 of a second, and we actually saved in the database as 0.003 of a second. So when you work with higher precisions with dates, it's recommended that you use either a date as a separate column, and time as a separate column, or you use datetime2. When we insert in date, basically the time on its own, we don't have that rounding issue. Also with datetime2, we don't have that rounding issue either. And basically this datetime offset is stored in the database as the time itself, datetime itself, plus the offset from the UTC. It's quite a useful, it's a very useful date type if you work, if you deploy the application globally, so multiple users. If you basically need to know the local time of the user and give all the data to the user in that specific local time, but yet you need to know what the offset from the UTC datetime was. And UTC being Universal Time Zone, so basically that's the 0 hour. All right, let's go back. No. Okay. The most common, of course, data type in SQL Server is strings or character fields. There are a number of basically options available, and if you look at basically char, that's a specific length field, and it actually occupies that much space in database storage. For example, if I declare char of 10 characters, it will take 10 bytes to store that field always. It doesn't matter, even if I save the data with about 2 bytes in it, or 2 characters in it, 2 bytes, it'll still occupy 10 bytes in the page in the MDF file. Varchar is called variable character field. So if I say, and basically n stays the maximum length of that field. So if I specify varchar 10, if I basically insert a data with 2 characters, it will actually store only 2 characters in the page file, or in the MDF, or in the page in the MDF file. And basically all the varchars stored at the end of the page and then if they increase in length, it carries them forward to the next offset page, etc. So nvarchar is called, basically it's a field to store Unicode characters, and I'll demonstrate the point of that. For example, if we want to store some Chinese or Russian characters, we need to use nvarchar, otherwise we're going to get some rubbish back, or basically won't be able to actually store that data. And Unicodes are always stored in 2 bytes per character. So basically the length of the field that it will be saved in storage is n, which is the maximum number of characters, multiplied by 2, plus nvarchar adds 2 bytes to each column as well. nchar is the same as char, but for Unicode. We can also store text and Unicode text as well. And text is basically a field that, well, basically data type that doesn't have the maximum length. We also have varchar and nvarchar where the n parameter can be max, which means that we can store up to 2 gig of data in that field. Yeah, it's 2 gig of data, which is the maximum integer number. And it's generally not very recommended to use max in the database, because when doing any kind of work with nvarchar max, the estimation plans, I mean, that's for those people who actually work with estimation plans, you'll see that estimation plans are going to look a little bit weird. I mean, in most cases, they'll just look a bit weird because you can't estimate the length of the field to do the proper rounding or proper string work with the data that you're working with. Right, so let's have a look at the example again. Right, I'll create a table with different data types there. I'll have char, maximum of 5 characters, varchar value of 10 characters, varchar max value, basically no limit, and text and nvarchar as well. And I'm going to insert a data into it, just 1 row. So the first column will sort hello, the second one is a little bit longer than hello, the third one is a lot of hellos, and basically in text we can insert anything we want. We can just basically insert a whole War and Peace, if it's going to fit into a gig data field. And the last one, this is basically nvarchar. I'll insert some basically foreign statement. Well, basically it's in Russian, some Russian characters. If we get this data back, they got inserted, all right, and in nvarchar field we actually get data saved and we retrieve it and we see the foreign characters correctly. If we then try to insert, let's say, this foreign characters into varchar max field, which is not nvarchar, which is not a Unicode data, this is what we're going to see. Question marks. And by the same token, let's look at, well, not by the same token, it's a different kind of subject. If we insert data that is basically that is smaller than the maximum character length specified in the character field, in character data type, we get that back, we get it. For example, if we try to insert a longer word into it, we're going to get a string truncation error. String of binary data would be truncated. And this data doesn't get inserted into the database. We can instruct SQL Server to truncate it and insert it anyway, but it's generally not recommended. The field doesn't fit into the specified data field. You shouldn't be inserting it, or it should be truncated on the client side in the right manner. All right, so going back to the character field. So for example, I inserted he into character field, and let's have a look at what it actually looks like when we get the data back. And what I'm doing here is I'm going to estimate its length of the field and data length as well. You'll see that they're going to be different. So the length of the field is 2 characters, which is right, it's only 2 characters, but the data length of that field is actually 5 characters. That's because this is a maximum precision for that field. Okay, and by the same token, if we try to insert stuff into data that doesn't basically fit there, we'll get a truncation error, but I've already shown that. Right, we have another useful data types. They're called basically image, binary, and variable binary. We're not going to. There's also SQL variant field, well, basically data type that we're not going to talk about today. But basically, image is binary, and variable binary allows us to store any binary data in the database. So, for example, images, any files, etc. It basically doesn't. I mean, image itself doesn't have the precision in it, and we can just basically stream data into the database directly. Well, into the database file directly using image and binary data types. That's a little bit more advanced. We also have a data type called XML, which allows us to store XML files in SQL Server and also query them as an XML file. So this is the example I want to look at. Let's look at the XML. Okay, let's create a table. And in that table, we have an object ID as a unique identifier. I'll talk a little bit about unique identifiers a little later as well. And we also have XML value, which is basically our XML file. And we're going to declare that XML as account, and within that account, we've got accounts. Within that account node, we're going to have multiple accounts. And within that account, we're going to have a name and a credit and so on, basically. And we're going to insert this data in the database. Okay, so if we query this table now, we basically have one row, and the data itself is actually stored as an XML. We can open that up, and we do see it as an XML. But more importantly, we can actually query it. We can query the database itself, each row individually, and we can query the elements inside the XML. So we do that by using the XML basically statements, because each field is treated as an XML. It has to be a valid XML to be inserted in the database, otherwise you're going to get an error. And what we can do, for example, in this scenario here, I'm actually going to select some data out of the database where XML value, and then here's the XML path where name equals first, and I want to get back the credit information for that field, for example. So there you go. Return 5655. So that's that value. So it's quite useful. We can also modify that data within XML, and in theory, it's actually working a lot faster than basically getting that XML, deserializing this on the client side, and actually doing stuff to it and then saving it back, because the XML OLA or OLE and SQL Server is actually basically reading that data and navigating through it node by node. Okay, but it's not very good way of storing data in the database. It's much better to basically break it down and store it in tables and index it properly. But if you've got some abstract data that you need to store, you're not entirely sure what the format is going to be. Like, for example, we have settings, user settings being stored in XML, because we don't want to create a specific data structure for those variable settings. So yeah, it's not very good for performance to store data like this, but it gives you a lot of flexibility. Right, the next one is actually unique identifier. I don't have that slide here. Anyhow, unique identifier is a 16-byte It's 16 byte, yeah. It's a 16 byte unique identifier that at the point of generation is going to be unique across, all over the globe. So you, in theory, you shouldn't be able to generate the same unique identifier anywhere else at any given time. So if you do something like this, which means basically generate me a unique identifier, this thing will be unique at any given time. So, no two computers can't produce exactly the same thing with exactly the same number ever again. So, in theory, I think it got like the maximum range we're gonna have, but it's gonna expire in like year 50,055 or something like this. It's actually based on your MAC address and your time, the way it gets generated. So because it's very useful data type to generate primary keys for the table, because we don't have to generate them on the server side. We can generate them on the client side and then save the data in the database. We know what those primary keys what they are. We know that they're unique across all the different databases. For example, we want to synchronize two different databases and they all have unique identifiers. We can easily just merge the data. We don't have to worry about the primary keys that author implemented. Basically, if it's a number, for example, if we have a customer in one database and customer in another database, and those customers have got IDs 1, 2, 3, 4, 5, etc., and the second database has got exactly the same IDs for the customer, and we need to take those customers and merge them together. It's going to be quite difficult because we then have to all the related data from all the other tables, what those customers bought, etc. When we merge them, we need to reassign those IDs. When we use unique identifiers, we don't have that problem because we just take that data and insert it into a different database. So the merging is quite easy. The downside of the unique identifier, over just an integer as a primary key, is the fact that it's a lot longer. It doesn't index very well, but we're going to talk about it later. Right. So let's discuss the relational data model. What it is actually, why we're storing the database. Why we're storing data in SQL Server the way we do. It's by far the most common way of storing data and querying that. It's called a relational database model. It's been kind of first formulated by a guy called Edgar Cott, and it's loosely based on first-order predicate logic. First-order predicate logic is actually a very fun subject, and sort of encourage you to go and look into that. It's pretty good fun. It's not. It is fun for me. Okay, and it's pretty cool because it basically defines the very abstract statements in a very logical way. So if we kind of take the academic approach to this and basically say what the first order predicate logic actually is. First order predicate logic is a way to represent semantic data by breaking down the statements into subjects and predicates. And predicates being something that defines what that subject does or modifies what that subject does. Okay, so we have first order predicate logic. We have subjects. This is a piece of data, and predicates. This is something that defines that data. So if we then look at it, we've got predicate, and then basically in brackets we put subject. The predicate is something that does something to that subject. Subject is being a piece of data. Okay. And for example, if I say something like Peter is a man, John is a man, and Matt is a man, as a separate statement, it's very difficult to make any kind of correlation between those two statements. So in first order predicate logic, we can define it as man, John, man, Peter, and man, Matt. So effectively, we can then merge them all together. We know that man, basically all of them are man. We can go even sort of further, and we can define that, for example, love being love, something that is happening or modifies, and then modifies whom? John, and programming what he loves to do. So we can say John loves programming by statement like that in first order predicate logic. We can go crazier like that, and we can also state that all, basically, this statement here, in first order predicate logic defines that all X, X being a programmer, loves programming. And basically, if we take that into RDM, relational data model, and we look at the first example when John is a man and Peter is a man and Matt is a man. So man is being our table, and John is being a piece of data that we store in that table. We expand that further on and we start creating relationships, like for example programming and John, and then what's actually happening between John and programming, all that kind of stuff. So relational data model is based around that concept, and there's a lot more information about it, a lot more examples, and it's kind of defined a lot more coherently than I can do here. So do look at it. Right. Let's go back. Right. When we store data in a database, we need to normalize it. We need to normalize it to avoid redundant data being stored in our database. The reason for avoiding the redundant data is to avoid update, insert, and select anomalies in a database. For example, if we can store everything as a big flat file, like we can do in Excel, for example. So we can say, we've got an order from whom, the address of the customer, and all that kind of stuff. But then imagine we need to modify a customer address, for all the orders. Then we have to actually run through every single order that customer placed and modify that address. But we need to delete all the customers, or all the orders belong to one customer. We need to delete multiple records, etc. So in order to avoid this, we segment the data table into multiple contextual parts. So we take every single duplicate in the database and basically break it down into smaller tables, give them IDs. There's a formal way of doing that. It's called normalization, and it's got 3 forms. Form number 1, if you delete you don't delete, you identify all the duplicates, you move them somewhere else, you give them primary keys, and so on. The normalization normalized form is second normalized form is something you do something else to it, and then you come to the third normalized form, and then happy days. In my opinion, the academic definition of how to do this is very kind of, as I said, detached from reality, and it doesn't really need to be that complicated. So if we actually look at unnormalized data table, so this is actually unnormalized to a certain extent. We do have some normalization to it because we've got order ID, but imagine this is it. This is just almost like a flat file. We've got order ID, customer name, customer email, customer country, so basically information about the customer telephone number, the source where the order came from, order dated, and total. So, and we start looking at this data, and so start breaking it down into contextual elements. Start seeing that order ID and order actually belongs to an order, and that's unique for every single order. Whereas stuff like customer can repeat itself because the same customer can place multiple orders. Then this is where I'm talking about detachment from reality from academic point of view. For example, in our case, customer telephone number could be actually grouped as the whole customer element, because if you think about it, the customer can only have one telephone number. Well, not really. A customer can have multiple telephone numbers. And that's what actually we store in the database. As you can see, myself, I've got 2 telephone numbers, 001 and 002. So basically that needs to be moved out of that customer context into another basic contextual element, being a customer telephone number table. And we also got source, which is also a contextual element that can be moved out of that table. So what we end up with is an order table first. So this is basically our I like to call it a header data. So everything else is basically related to the order table. Okay. So let's start normalizing the customer bit. So as you can see, we've got customer, and the customer's got name and customer email. Let's imagine they are unique. Again, we might have a situation we've got multiple customer emails. But in this case, imagine it's just one customer email. So customer name and customer email is a unique field for every customer. And then the customer country actually can repeat itself. Okay, in this specific scenario, I just got like, 3 different customers from 3 different countries. But in theory, there might be different customers from the United Kingdom as well. So it's a good idea to go and take customer country and move it out as well, and it's a contextual element, group them together, give them, and basically also group customers together, and give customers IDs. So for example, I acquire a new ID of 1, then Peter 2, and John at 3. And then finally, we also need to basically bind a customer to a country, so relate a customer to a country. And then we give country ID, and we basically insert that ID to a customer itself. So the purpose of doing this is, imagine we need to modify, add a new field to a country. For example, we need to define a country zone. So if we stored basically each country against the customer, then we would have to modify the customer data. The customer database, customer data table, and for each country, each customer would have to insert that customer's data zone as well. Country zone. Whereas if we break it down, then we can just insert the country zone for the country itself, and then because they are related to the customer, we actually have the country zone specified for the customer itself. Right. So we now have the order. We kind of split out the customers out of it, and we also split the countries out of the customers. And remember I mentioned about the telephones. You can have multiple telephones for the same customer. Now what we're going to do is we're going to take the customer ID and insert it into the order table. So we now can relate each order to a specific customer. Okay, so the next bit is the telephone numbers as well. So what we're doing is we're going to take the customer effectively and relate them to telephone numbers. Because we've got basically different, multiple telephone numbers for a customer, and each order placed should be related to not only to the customer but also to a telephone number as well, in case the customer places that order and he specifies a different telephone number. So what we actually need to do, we need to store the telephone number and the customer in the order table. Because if we don't store the telephone number and we just store the customer name and customer and the multiple telephone number against the customer, we get data. It's not collision. It's called. I forgot what it's called. Basically, it means that we can't tell what telephone number we should use for each specific order. Right, so what we're doing is we're going to take the customer table basically and take all the telephone numbers for that customer, and we're going to make a new table called telephone number ID, and we're going to relate that to a customer, and we're also going to insert the telephone number ID in the order table. So that's how we can know which telephone number to use with which order. Right. So I have already normalized the table. So this is basically so we start looking at some examples, and what I want to sort of look at is what's a primary key, what's a foreign key constraint, really. So this is our unnormalized data. Let's switch the database. Use normalization. Go. Okay, so this is our unnormalized data. I normalized it into order. Customer and country and telephone numbers. Okay, so At the moment in database, I don't have any. Oh, telephone numbers are empty. Anyway, so at the moment in database, I don't have any primary keys or foreign key constraints, which means basically my database is loose, we would call it, which means I can insert any old rubbish into any of those tables and it's all going to be fine. But once I start doing some kind of selection out of it, I'm not going to get this data back out of the database. So to give you an example, let's insert a new record into order. Specify the columns. Always specify the column names. Okay. Right, 6. Order total is going to be 100. A customer, I'm just going to come up with a number, 55. That's the customer ID. And telephone number, just going to insert 1. And source ID, let's say it would be 1. So actually the first one is customer order date. Can you put the aircon on? It's really hot. Okay, so before we insert the data, let's actually go and select all the data from orders, and we're also going to join it to customer. Order, customer ID, and order customer ID. If I join it, it's all fine basically because I have the relationship between the order table and the customer, and all the customers that are specified in the order table actually exist in the customer table. So that's all good. But then if I insert some rubbish into it, well, it's not rubbish into it, and you insert a real order from a customer ID 55, and the customer ID 55 doesn't exist in our customer table. So without any constraints in the database, it's all going to be fine. I can insert this data. And if I just look at the orders, I see that record there. There you go, it's right there. But if I start joining to a customer table because the customer ID 55 doesn't exist, I don't see it in the results set at all. So to avoid things like this, to basically provide data consistency in the database, we insert constraints. Well, we basically add constraints to the database. Constraints being we define what are the relationship between different tables, and you can't insert basically data with the data basically where the relationship doesn't exist. Right. So another thing is we need to basically define constraints. We need primary keys on each table, so we need to uniquely identify each row by its ID. And as it's already mentioned, we can have, basically those primary keys can be an integer, they can be varchars, but you just have to make sure that each row is uniquely identified with that primary key. Most common ones are integers, of course, just an auto increment. So we can have an auto increment on the table when we insert new data, then the number gets populated by 1 or by a seed number. So for example, we can say increment it with every row by 5 or etc. But we can have unique identifier. Unique identifier you just produce on the client side or on the server itself, just say new ID, and you insert it in the database with that new ID. It's guaranteed that it's going to be a unique ID. Or with auto increment, the server itself will handle the incrementation of that field, and it just basically can insert data. So once I created the structure of the database as is, inserting some data into it, there's no way I can take one field, for example. Well, I can take one field in that data table and say this is going to be our primary key. That's fine, that's okay. But once we kind of created the table already, we can't modify it to say this is going to be an increment field. So we have to do it as backwards by basically creating a new table and then copying the data, basically creating a new table with a new structure, new constraints, all that kind of stuff, and then copying the data out of that out of the old table into a new one. That's pretty much exactly what we're going to do. So the whole purpose of the next exercise is to set order ID as a primary key and also define it as an auto increment number. So let's start breaking this down. First of all, I'm going to create a new table. I'm going to call it order new. And in here, I'm going to define exactly the same structure that I had in order table, but with one exception. Order ID I'm going to have as identity 1 by 1, meaning that I'm going to have the identity field starting from number 1 and incrementing by 1 every time I insert new data. So creating this table. The next bit, I need to specify a constraint. Basically, I just have to specify which column, basically, which data field is our primary key. So alter the table and add a constraint, give a constraint a name, and then specify that this is going to be our primary key, and specify a column which will become our primary key. There you go. So now that I've got order ID, let's have a look at the table itself. So this is our order new table, columns. As you can see, I've got that little key sign next to it, meaning that this column is our primary key. And in keys, I also get the constraint itself, so that's our primary key. And so now I can just basically go and insert the data into this table from the orders. So if I try to do that, it actually tells me that I can't do it because our order ID is auto increment identity. So I can't just insert any data that I want in it, because that field is supposed to be incrementing by itself. But in SQL Server, I can say, you know what, turn that functionality off. I'm going to be providing the data to you. So, and you do that with set identity on that table as on, meaning that I can insert my own identities. And then now I can just go and copy the data from, so with this statement, I'm inserting data into order new table from this table, from this selection. So I'm just selecting all the rows or all the columns from order table and inserting that into order new table. There you go, it inserts them happily. And then I need to go and turn the identity off. Okay, so let's select data out of it. There you go, we've got it. We've got it in there, and then what I need to do now is I need to drop the old order table and then rename the order new table into order table. So drop in table, easy, and then sp rename renames the table. Okay. From order. There you go. Let's do exactly the same thing with customer as well. So in order to establish a relationship between two tables, I mean the parent table, not a parent table. Basically, the primary, both tables have to have primary keys. Well, actually, the table that you're referencing has to have a primary key. We have to uniquely identify each row, and a foreign key can only become out of a primary key. So if we want to say that our customer ID is a foreign key of a customer itself, then we need to make that customer ID a primary key. And also I want to do exactly the same thing. I want to make sure that this customer ID is an integer with auto increment that gets populated every time we insert the data. So we're doing exactly the same exercise as we did with orders, which is let's create a new table, set a primary key on it, copy the data from the customer, drop the table, and rename it. There you go, that's our new table. So now if I insert a new customer into this data table, go in, Right. Customer ID. Well, I don't need to worry about that because it will auto increment. Country ID, just one. And we'll say, I don't know, Tim, wherever Tim is. Okay. Right. So Tim now has got new ID 4 because it's been auto incremented. Right. So now I've got order with a primary key. Let's make sure that it is. No, that's orders. This is it. Order and a customer. So what I need to do now is to define in a database the fact that order always has to belong to some sort of customer. So customer has to exist before we insert the order. And I do that by basically creating a constraint on the order table. So alt table, meaning that we're going to do something to a table. So we're going to modify it, order, then we add constraint, the name of the constraint. We'll say that this constraint will be a foreign key on the field customer ID, and it will reference customer table and a customer ID in there. From here, you can kind of start picking up the fact that the first order predicate concept, customer being a predicate and customer ID being a subject, and so on. Basically, as I said, I strongly encourage you to look at first order predicate because you start understanding not only how the database works, but how many other things in computing actually works. And it's actually a good exercise for your brain to start basically encoding different statements about the world in some kind of logical form and actually making derivatives out of those predicates. Okay, so if I try to run this statement now, that will fail because do you remember previously I inserted a row in our database with customer ID 55. So basically, straight away, it basically tells me that there is a problem with the order table that contains a customer that doesn't exist in our database, or in our customer data. So to make this actually work, I need to go and delete from order where customer ID not in customer. So that will basically give us all the unique IDs of all our customers, and that will delete all the orders that where customer ID is not in our customer data table. So just one row, and now we can enforce that constraint. Once we enforce the constraint, we're going to have a relationship between those two tables. And we can visualize that by using the data diagramming tool. Let's insert customer and order. And now we have this relationship between those two tables. And that relationship basically stating that there is a primary key on the customer table, and it's got many customers in orders. So that's a relationship that is called one-to-many. By the way, this tool, data diagram tool, is basically a tool where you can actually create, where basically you can modify the tables themselves, and you can actually create different different constraints yourself as well. For example, I can go and add a source table, and I can say source ID will be our foreign key constraint, all this kind of stuff. So instead of actually running this as statements, we can do it in diagramming tool. Don't ever do this. Don't use the diagramming tool for anything else other than looking at the structure of the constraint, visualizing the constraints. Don't ever use this tool to modify any data. It's dangerous. The same as it's dangerous to use visualizing tools to create queries. This is even more dangerous because you're actually using the VDL, so you're actually modifying the data structure with this stuff. Okay? So there you go. This is something to be aware of. It's there. Don't use it. Right, so now we've got a constraint. If we try to insert data into the order table again, for a customer that doesn't exist in our customer database, the orders. So first of all, we don't need order ID anymore because it will be order incremented. The date is going to be think customer ID, let's say 55, telephone number just 1, and source is 1. So I try to insert it, it doesn't exist. I mean, basically throws an error to me. It's not going to insert the data because there's a constraint on the tables that don't allow us to do this stupid things anymore. So now let's insert someone real. Now I'm inserting him, and then I need to, in fact, let's go for a different example. Imagine I need to insert a new order for a new customer. So let's create a new customer. There. Again, let's get rid of customer ID because it will be incremented. Values for United Kingdom, and this customer is going to be Nick. Okay, so this customer is placed the order, and then I need to insert a new order for this customer. First of all, I have to insert the customer into the database before I insert the order, because we've got a constraint now. We can't just do it the other way around because it will fail. So again, new order, and the values for that order would be some date, you paid a lot of money, and then I need customer ID, but I don't know that customer ID because I'm inserting this guy here first. So in theory, I should insert this data first, get its customer ID out of the database, out of that newly inserted data, and then populate it there. Well, when we insert the data, SQL Server has got this identity field that basically, once the data is inserted, it will assign a local variable within a session that newly inserted ID. And we can get that by declaring a variable. We declare new ID, and then setting that variable to identity field. I think it's called actually scope identity. Yes, scope identity. No, sorry, it's going to be identity. So once I inserted the data into the customer database, new variable, this new ID variable will actually acquire its newly inserted ID. I'm not going to use this to insert a new row for Nick for some source. Okay, let's run it. So look at the data. So there you go. Nick got a new ID 5. And we've got a new order for Nick for that amount. Customer ID is 5, so that's our identity. There are different ways of actually getting that identity. There's scope identity, identity itself. There is last identity and the previous identity and the whole raft of things, but generally that's how you do it. Right, well, that's about it. Any questions? Yes. To be honest, I'm not entirely sure how the data time tree is actually stored in the database, because in my mind it doesn't fit within 6 bytes. Any other?
What is the next lesson?
I don't know yet. Yeah, now we're going to start actually connecting to the database from a third-party application, start actually running and looking at the SQL selects, and start looking at the more advanced structure of databases, how to actually pull the query the data, how to insert the data in the right manner, etc. So it's going to be more from a client application to the SQL Server, and how to create queries properly as well. So this stuff is just a foundation, so that everybody's on the same page as everybody else. And I'm pretty sure that a lot of the developers themselves, they don't really know the normalization that well and how to break things up.
I have a question, but maybe I can explain it, but anyone maybe it will be something difficult to other people. Why the store prices is low? I don't understand. Because it's not precise, no.
It's not. It's precise enough to store. So basically, they get the pricing information. One of the reasons why we store it as float is because it's easy to work with from C#. Because you get a double back. You don't have to do any conversion. It's just a double. It's the only reason for it.
But double is not precise, double is low.
It's precise enough, yeah. And floats are generally faster to work with than decimals. In terms of the computation itself is faster. Also, it takes less space on the server as well. If we go back to our slide, actually they're not. Decimal of 7 digits, float of 7 digits is 4 characters, and decimal with a minimum precision of 18. This is the minimum and the default precision that is recommended. I'm sure you wouldn't know, you wouldn't need 18 digits in the field, but yeah, we don't want to end up in a situation when somebody, bought with Zimbabwean dollars for $50 billion. Dollars, and we can't insert that data into the database because our fields don't handle that amount. With floats we can. So even we use the precision of about 18, we're going to be occupying 8 bytes in storage. And obviously when you're doing any kind of arithmetics on it, it matters greatly. But yeah, decimal generally is a better way of storing data, especially for things like monetary values and things like that. You're absolutely right. But it's pure laziness. You don't want to get stuff converted.
I only noticed because I'm working on a new channel, and I noticed that sometimes the price gets rounded down or up.
Well, that's the thing. With decimals, it will get rounded up and down. But with floats, it won't. It will carry as many decimals, as many decimals as it can. Yes, if you start doing the arithmetics on top of it, then you start basically seeing some fluctuation in the floating point. But generally, it's even a good thing when you start working percentages. It's better to use not precise numbers, but approximate numbers. That it?